in Moscow. And this work began with a few observations that we made about the quantum cohomology, the small quantum cohomology of certain homogeneous spaces. And we realized at some point that the classical story was related in a certain way with the Satake, the famous Satake correspondence. So actually a very tiny and elementary bit of this correspondence, but still a surprise, and what I will explain is that some of this part extends to quantum cohomology. So I will begin with a very elementary reminder about essentially Grassmannians and their cohomology. And then I will explain the connection with, try to give an idea of this this Satake correspondence. And then I will explain how this extends to the quantum cohomology setting. So this will be the plan of my talk. So let's begin with the Grassmannians. So that's a very classical story. So you probably all know about that. So my notation would be RKN for the Grassmannian. Of k-dimensional subspaces of n-dimensional space. And then there are two ways to understand the homology of the cohomology of the Grassmannian. So one is in terms of the Schubert classes. So let's say over C. So there is a preferred basis given by Schubert classes, which are those which make sense in when you do enumerative geometry. So these are the classes of the so-called Shubert varieties. Which are subvarieties defined in terms of incidence conditions, so that I will not recall. It's not so important for this talk. And this set of lambda here, lambda is a partition. Traditionally, the index set of Schubert classes is the set of partitions so non-increasing sequences of integers, k of them, bounded by a minus k. So this is the index set. So there is also a polynomial presentation of this cohomology ring, which you get, for example, for the from the tautological sequence of bundles. So there is the tautological k-dimension rank k bundle, which is some bundle of the trivial bundle, and then you have the quotient rank minus n minus k bundle. So you can look at the Chern classes. So you have the classes of the say the dual tautological bundle, and then you can also consider the classes of the quotient bundle. And these classes are enough, as you all know, to generate the cohomology ring. So maybe just you can write it like this. You can use these classes as generators. Then you have, this is nice because the relation is very easy to write down. just the fact that because of this extension, this product must be 1. And you can also use these relations to eliminate the classes of the quotient bundle, for example. So you get more traditional description of the quotient of a ring of k indeterminates by some relations. At k relations in degree n minus k plus 1 up to n. So the multiplicative structure given by this description is very, very simple. And all the problem when you do enumerative geometry is to understand the interplay between the additive structure and the multiplicative structure. So this is has been known for a long time, of course. So for example, you have formulas like the Pierry formula, which will only state the first one, which tells you how to multiply some Schubert class by C1. And this is just a sum over the partitions that you obtain starting from lambda by adding 1 somewhere. So you note like this the fact that you add 1 to the ith part. And if you want this to remain a partition, you need that lambda I be greater than lambda I plus 1. Okay. So there are similar rules for product by the other classes. And then after some work, you can deduce what is really interesting in enumerative geometry, which is how you multiply 2 Schubert classes. Okay, so this is these are the little Richardson coefficients. And so this has been there are many different combinatorial rules to describe these coefficients. Some of them have been known for quite a long time. Some of them are rather recent. And so I want to point out that although this is very classical, once you try to go beyond just the case of the Grassmannian and treat some other homogeneous spaces, things can become much more complicated. And there are still very active research even in the classical setting and of course in the quantum setting. But even for in the classical setting, we don't have a full generalization of this little rule Richardson rule for whole homogeneous spaces, and that's something which is really missing. Okay, so this is maybe the mainstream of research on these homogeneous spaces. So there have been important contributions from many people, including some in the audience. But what I would like to explain is a slightly different perspective. Which is related to something also extremely classical and elementary, which is the Plücker embedding. So there is this preferred embedding of the Grassmannian inside a projective space, which is the projectivization of the kth wedge power of Cn. And here there is you can notice that if you can choose some basis of Cn. And then you got some natural basis of the wedge power, of course, which I denote by E lambda. So you take the product, the wedge product of K different basis vector. And the natural way to do this is to index them by, again, partitions. So you get exactly the same index sets, same index set as for the Schubert classes. And the observation, the very first observation that one can make is that, so you have this correspondence with Schubert classes in some way. And then there was this Pierre formula here that I wrote on this blackboard, the very first one. You can see it as parallel as a formula here, which is, well, if you look at the corresponding sum, this is just the action of lambda of some operator x which in the basis of Cn is this nilpotent matrix. Okay, this is an SLN module, and you can rewrite the first Pierre formula as given by this action of this very simple operator x. Okay, so this could be seen just a coincidence, except that maybe this, you can notice that this operator has a very special role in Lie theory. So x, so it's a nilpotent matrix. It's a generic nilpotent matrix. And written like this is called a principal nilpotent. And it plays a very important role in many issues in Lie theory. In particular, yes, right, that's correct. Then the next one would be UH2 plus k minus 1. So you would write them as I1. So you could just take a wedge of k different vectors, then you can impose that they are like that. So you could choose this convention, but then you write. I change a little bit the indexing. I denote I1 by lambda 1 plus k, etc. So the strict inequalities become large inequalities,
okay, so
and I get a partition.
Lambda k would be somehow, so could be equal. Lambda 1 greater or equal to lambda 2?
No, so they cannot be equal, because I have lambda 1 is larger or equal to lambda 2. So this one is big.
Lambda 1 and lambda 2 is only greater or equal, and so you push that a little bit. So
Yes.
So should I think of E lambda as the image of, say, a general, the central point of the cell sigma lambda, or something like that?
Yes, exactly. It will be the case, yes.
And the open stratum is lambda equals 1, 1, 0, 0, 0, 0.
It depends of your convention.
Well, no, but you fix the convention with the Pierre formula.
It depends on. Okay. You can make the choice you want. Okay, so yes, what I was pointed out is that there is something analog in any simple Lie algebra. If you take G any simple Lie algebra. So what you do in general is fix a Cartan subalgebra. And then you get the roots space decomposition. Okay, so you diagonalize the action of the Cartan subalgebra. You get some one-dimensional eigen spaces, which are indexed by the root system. And then you choose a half space of positive roots, and then you have the simple roots. And you can write, then you can choose some generators here. And then you can write the generalization of this principal nilpotent is the sum of the root vectors corresponding to the simple roots. So delta is my set of simple roots. Okay, and so from the formalism of a root system, you can write down a preferred nilpotent element, and it's known that the nilpotent set of nilpotent elements has an open orbit for the adjoint action, and this is a generic nilpotent element. And it will play the role of this. So this is a special case in SLN if you make the suitable choices, and this is the natural extension of this. And this element turns out to play a role in this Satake correspondence that I want to explain now. So I just want to give you an idea. I will be a bit vague and imprecise, probably slightly incorrect at some points, but at the end I will use only a very elementary part of this correspondence, and the objects will be quite simple. So the Satake correspondence is constructed from the affine Grassmannian. So you start with the, let's say, semi-simple complex Lie group, and then you introduce the loop group. I will take as the space of maps from C star to G. Okay, so this is naturally a group, infinite dimensional, and it contains the maps that extend to C. And you can think of the affine Grassmannian as the quotient. So that's a homogeneous space, again infinite dimensional, and in some way it is you can identify it with the space omega. The group, so let's say the set of based loops in K. So I mean really the loops in the usual sense. So maps from S1 to K. Let's see. Sorry, let me say something more correct. So you look at F in LG, which have the property that F1 equals 1, and that the unit circle is taken to K, which is a maximal compact subgroup of G. Okay, so there is a natural bijection which is between the affine Grassmannian and omega. And this is important because this shows a very important difference between this infinite dimensional case and the usual case of homogeneous space. Space is namely this is a group. This quotient is again a group. So for example, its cohomology will have more structure and it has many important consequences. Okay. So you must think of this as really a generalization of the Grassmannian, except that it is infinite dimensional, and it has this nice property which does not exist in the finite dimensional setting. And then you have the Schubert varieties. So the Schubert varieties are constructed from there will be the orbits of special points in the affine Grassmannian, which correspond to special maps from C star to G, which are just the one parameter subgroups. So you fix T a maximum torus, and then you so the space of one parameter subgroup, or is naturally a subset of the affine Grassmannian. And then you look at the orbits of the so definition is you take the orbits of lambda for lambda such so this is the traditional notation, and you look at the orbit. So it turns out that also the affine Grassmannian is infinite dimensional. This is finite dimensional, and the Schubert variety corresponding to lambda is the closure of this orbit. Okay, so this is the affine Schubert variety. So it turns out that these affine Schubert varieties, they are almost always singular, and badly singular, actually. So you can, what people have been considering is the intersection cohomology. So which is a kind of substitute for the usual for the usual cohomology, which is much better behaved.
Sorry, can I check the definition of all lambda? Is you pick one parameter, you pick an element with one parameter subgroup, and you
Yes, so I see it as a point of the affine Grassmannian. It's defined a point in the affine Grassmannian, and I take the orbit of LG plus. Okay, so remember that the affine Grassmannian is homogeneous under LG, and I have this. I look at the action of this subgroup of regular loops, and I take the orbit. In the affine Grassmannian. I have taken the quotient, but still I have a left action of the group LG. Yes, I have the left action. So I take the orbit, and then the closure gives me the affine Schubert variety.
And it's finite dimensional.
Finite dimensional, yes. It's a projective variety. Okay, and then the Satake correspondence is that so I will state a version which is contained in a paper by Ginsburg from 1995. So it says the following. So you can look at the take the Langlands dual group. So essentially, this is constructed from the dual from a maximal torus which has the property that its characters are given by the co-characters of this one. Okay, it exchanges the characters with the one-parameter subgroups. So this is this space of homomorphism from the torus to C star. This corresponds to the co-characters, one-parameter subgroups of T, and then the characters here they index the irreducible representations of the group. Okay, so if I take my lambda here, it defines an irreducible representation of the Langlands dual. Okay. Then the correspondence is then you can reconstruct the you can say it in different ways. You can recover the representation, the category of GL modules in terms of this intersection cohomology complexes. Or here just you can identify the intersection cohomology of this X lambda with these representations. So there is something rather explicit here. So you can state the Satake correspondence as abstract equivalence of categories, but there is something very concrete in this correspondence, which is this identification. And so what does it really mean that we identify these two spaces? Well, let's hear that the principal nilpotent will play a role, because so you take X principal nilpotent in the Langlands dual, the algebra. And you take its centralizer. Okay, so for SLN, it will be just this algebra of matrices with content terms on the inferior diagonals. And because of the structure of the affine Grassmannian, its cohomology has a very rich structure, and it was proved by Bott that it can be identified with the enveloping algebra of A. Okay, and then this tells you how this identification works, because you have a natural action. X lambda is contained in the Grassmannian, so the intersection cohomology comes with a natural action of the homology of the affine Grassmannian. So you have a natural action here. And then this is a GL module, so also a module over the enveloping algebra. So you get an induced action on this. And Ginsburg tells you that these two actions can be made to coincide. I get only this action at this point. I mean that I can show you explicitly the identification for UA, yes. The action is natural on both sides for this subalgebra. On the left-hand side, it's really cohomological, and on the left-hand side, it's really representation theoretic. And you can match both because of this Bot's isomorphism.
Sorry, so it's UG dual module, but the X
Yep.
lambda is using the G to construct, right? X lambda is for G, and then but the action is from G dual.
Right. But the identification here, there is the duality. A is in the Langlands dual, right? At the level of A is contained in the Langlands dual, the algebra. Okay, so in fact I will need this only in the case when the affine Schubert variety is smooth. So this happens in very few cases, but still this happens. Maybe I can use so there are some minimal affine Schubert varieties which are smooth. So it turns out that the smooth affine Schubert varieties are the some special homogeneous space which are called minuscule. So there is a short list actually. So there are the Grassmannians, the even dimensional quadrics, the spinner varieties, and then there are two exceptional cases. And they are called, the terminology minuscules comes rather from the representation theoretic setting. From a property of there is a preferred equivalent embedding inside some representation, which is always a fundamental representation, denoted by the omega. And this is what is called a minuscule representation. And this property means the following. So when you look at some representation, you diagonalize the action of the Cartan subalgebra. So you have the theory of weights, and there is an action of the Val group on the set of weights. And minuscule means that the Val group acts transitively on the set of weights. So you have the highest weight. No E8 case. So you have the highest weight, and you have the images of the highest weight by the Val groups. So the weight of the representation, they are indexed by the coset of the quotient of the Val group W by a subgroup, which is the Val group of the parabolic P. Okay. So I can apply the Satake correspondence to these minuscule homogeneous spaces, and it tells me that I have a natural identification between two rather different objects. So I restricted myself to the simply laced case. So just so you will not hear again about Langlands duality, so that make things a little simpler. So you get an identification between, well, this is smooth, so I can take the ordinary
minuscule representation, say if I'm taking the parabola supposed to be Borel, what would this be?
Oh, no, it's never Borel. So P is always maximal. So the Picard number is the Picard group is Z. So except for SL2, it's not Borel. So you get an identification between the cohomology algebra and the representation. Okay. So you had a priori two very different objects, an algebra on the left-hand side and a G module on the right-hand side. Okay, and the identification is so there is a natural action and action of this A on both sides. Okay, so that's what I showed you explicitly at the very beginning. And I took this, in the case of Grassmannian, this principal nilpotent. And you've seen that the Pierre formula here coincides with the action of X on the right-hand side. So this is a manifestation of this Satake correspondence. Okay, so let's see what happened at the level of quantum cohomology. So there are several facts that make the situation very, very pleasant with the quantum cohomology of minuscule spaces. For example, so there is something very general which tells you how to describe the classical cohomology of a homogeneous space. So this is the Borel presentation. So you take any G mod P. Then you can write the cohomology as, so you take the Cartan algebra T, you look at the polynomial function on T, you look at the WP invariance, and then you mod out by the W invariance of positive degrees. Okay, so this tells you in very general setting what is the multiplicative structure. And so by Chevalier theorem we know that this algebra of invariance is a polynomial. So this is a polynomial in our generators that can take homogeneous of degrees d1, dr. And these degrees are very important. They are called the exponents. Oh gee, there are very important invariants that appear in many different contexts. So in particular, the largest one has a especially important role. It's called the dual Coxeter number. So something nice that happens here, which is not very specific to minuscule spaces, is then H is also the index. So the anti-canonical is H times the hyperplane class. So when you look at when you consider the small quantum cohomology, H is the degree of the quantum parameter. Okay? So this implies that, so you know that the quantum cohomology will be obtained from the classical one by deforming the relations. And since the highest degree relations has degree H, which is also the degree of the quantum parameter, you don't have much choice. This means that the quantum cohomology will be okay, so there are some generators. I denote like this, the quantum parameter, and then you mod out by the relations. The quantum relations, which are obtained by modifying just the relations of maximal degree. So if you normalize correctly, you get this presentation.
How do you know coefficient is negative 1?
Just normalization. I can normalize in such a way that the coefficient is like that. Yeah, so by this argument, you just have to, there's just one coefficient to compute in order to find the coefficient. So let's say we have computed it. Okay, and so this gives the multiplicative structure. So from this you can deduce that this is a semisimple. So let's say for Q equals 1. So for Q equals 0, the classical cohomology is concentrated at 0, so extremely far from semisimple, but the quantum cohomology becomes semisimple, so which is not true for all homogeneous spaces, but in the minuscule setting it is true. So this was proved by Chaput, Perrin, and myself by some case-by-case computations, but there is a nice argument by Gorbunov and Petrov, which noticed that there was a connection with some important work of Constant from the 50s.
I have a question. So when you say Q equal 1, what is the radial convergence for small quantum cohomology?
Oh, it's Fano, so
It's 1, right?
it's Fano, so
Oh, it's Fano, okay.
So what's the relation? Well, a very classical fact is that when you look at all the invariants, so I have to remind you of the Chevalier isomorphism theorem, which is that these spaces that are considered of double invariant polynomials in T, this is isomorphic to the space of G invariant polynomials on the Lie algebra. Okay, so you can, so these relations, I can see it as polynomials on the Lie algebra. And it's a classical fact that if the set of elements for which all these invariants vanish are exactly the nilpotent elements. So X is nilpotent. Maybe Y. So now I have something slightly different. All the relations vanish except the relation of maximal degree. So this is a definition due to constant that an element is cyclic. The relations vanish up to the last one, and the last one gives you non-zero. And Constant proved that these cyclic elements are very well behaved. So they have so for example, the G orbit is determined by exactly this non-zero value. Moreover, he proved that cyclic implies that we have a regular and semi-simple element, which means that when you look at the centralizer, this is a Cartan subalgebra. And then you can look at the action of the Weil group on this Cartan subalgebra. And it proves that the action of let's say the W orbit of Y in this Cartan subalgebra is free. There is no stabilizer. So now I can rephrase this statement on the quantum cohomology of G mod P. I can identify this with the space of functions on this orbit.
Sorry, when you say W orbit of W orbit O
Sorry, of Y. So now I can identify the quantum cohomology of G mod P with the space of function on these orbits, which are WP invariant or to the quotient. Okay, and this is semi-simple because the orbit was free. So what is also nice that you can so cyclic elements are simpler than nilpotent elements because there are many nilpotent orbits. Here we have only one G orbit for each value of the invariant. And Constant gave an explicit representative of each orbit. You can, just by modifying slightly the principal nilpotent. So you can, so I had the, so remember I had data the simple roots. And there is a highest root, which I denote by psi. And then you can define xq as So the same element, the principal nilpotent I introduced before, and you add, it's a q times the root vector corresponding to the highest root. So the claim is this is cyclic, and this gives you representatives of all the g orbits of cyclic elements. Okay, so of course for the SLN case you will get same thing as before up to this little q here, which makes it cyclic. So maybe I can state the main theorem. So one can define a map theta from A to let's say to the classical cohomology. Should I extend that? Okay, so I'll be a little vague and identify the quantum cohomology and the representation. So in such a way that so for any y in A, the quantum multiplication by this element corresponds to the so this is a Lie algebra action. Okay, so I have quantum multiplication on this side, Lie algebra action on this side, and this pi q is a natural isomorphism between A and what I denote by AQ, which is the centralizer of this XQ. Okay, so you see, so this is almost, so this is the quantum generalization of the quantum Satake of the Satake correspondence in the minuscule setting. So you have the action of A on both sides. On the cohomology side, it is given by theta. On the Lie algebra side, it is given just by the embedding of A inside the Lie algebra. But in the quantum setting, you have to modify a little bit through an isomorphism between A and AQ. So there is an important difference here, which is that A is an abelian, but not a Cartan algebra. And here you get a Cartan algebra. And this is a key point in the proof.
Sorry, what is AQ?
So it's a centralizer of this cyclic element XQ.
Oh, you define it as XQ, and then
Okay, so In the classical setting, you get q equals 0, so you just have A, and you have the statement. So in the quantum setting, you just have to change. You don't change the left-hand side. Theta is always the same. It does not depend on q. But you just have to twist by this. There's a natural isomorphism here between this algebra and this Cartan subalgebra. And this is the only thing you have to do. Just change A into AQ, take the natural isomorphism.
So C of SQ is that isomorphic in the non-conjugate way?
This is a Cartan subalgebra for Q non-zero.
I'm kind of confused by the statement here. So both sides you have a q variable there, right?
Yes.
So what do you mean you say the q equals to 1?
Yeah, okay. So Q is fixed, but
So, okay, you don't really just say q equals 1.
otherwise I could twist by the space of polynomials in Q. So that's for fixed Q. And maybe to conclude, I want to say that this is completely explicit, actually. You can really, it's completely explicit. You can really, this A is graded in some way. There is not kind of natural grading by some, so it is generated by some classes which have natural degree. So theta of A, theta of, if I apply theta to these classes, I get a cohomology class of degree 2di. And I can really read these classes in terms of the root system completely explicitly. And then I can and also by Q, I don't have time to explain it. In terms of root system, this is completely explicit. So you can get the formula you get is you have these preferred classes, PDI, and you have a completely explicit formula. If you want to multiply PDI by some Schubert class, say, well, there you apply YDA to E lambda, and then you have some quantum correction, which is only linear, which is given by a completely explicit operator. So in some way there is something a bit tricky here, is that you need to see these classes as acting from outside, in fact. This is a quantum multiplication, so you can believe you are inside the quantum multiplication algebra, but it's rather an action from outside, really from the universal enveloping algebra of this A, which is, so theta is something inside the cohomology, but it's a kind of external action. And you don't see the affine Grassmannian anymore, except that, so if you're used to root system, once you add psi to the simple roots, you get the affine linking diagrams. So you're really closely, directly connected to the affine Lie algebra and this kind of setting. So this is how you see that the structure comes from the affine Grassmannian. So it's not so much surprising in the end, since the affine Grassmannian parameterizes loops, and loops are not so different from genus zero curves. So, of course, the next question is that this works only for minuscule, so for the smooth affine Schubert varieties. And you can wonder what happens for the other affine Schubert varieties. So is there any extension of intersection cohomology to the quantum setting? So maybe. Thank you.
Is there any questions?
sounds very much like you are doing really like a mirror symmetry. This is a quantum homology of a homogeneous space. Other side representation theory. I don't know. Maybe there are some kind of line of things, but mirror there. This were the natural place. Those representation theory would lead.
I don't know that. There are certain homogeneous spaces for which the mirror is known, but I'm not aware of any.